In that essential understanding box, it's saying the degree of a polynomial tells you how many roots an equation will have. Yes, we did that. We looked at a quartic and we said, okay, we should have 4 answers. We've been doing that. And it's easy to see that in some polynomials, but then these examples here, it says there appears to be 3 possibilities for a polynomial of degree 2, and they correspond to these 3 graphs. Tell me this, how do we know that that's a polynomial of degree 2? How do we even know that those graphs represent a degree 2 polynomial? Catherine? Exactly. And a quadratic is always going to be a parabola. So we've got 3 equations, 3 different graphs. So we know the zeros of a graph, or the roots, are where your graph crosses the x-axis. So, quadratic, degree 2. The first one makes a lot of sense. We cross twice on the x-axis, meaning we would have 2 real answers, or 2 real roots, or 2 real zeros. Remember, all those words can be used interchangeably. Now, if you look at the middle graph, it only crosses the x-axis once. So, according to that graph, we have 1 real root. And according to the third graph and its x-intercepts, how many real roots would we have? Rachel? Exactly. But why would this make sense? Why would this even be possible? We just said if it's quadratic, degree 2, it has to have 2 roots. And the only one so far that has 2 roots that we can see is this first one. What about these other guys? Aren't they supposed to have 2 roots? They are. They do. How do those have 2 roots whenever this one looks like it has 1 and this one looks like it has none? Think about what we've been doing. Think about some lessons back. Andy?
Imaginary roots.
Exactly. When we have no real roots, so we have no real solutions, then we have imaginary solutions. So for our third graph, we have no real roots, but we have 2 complex roots, meaning they use imaginary numbers. Okay, what about the middle one? It's not imaginary because it's there. It's right there at 1. We can say that that solution is 1, Steve.
1 complex.
Nope, they're both going to be real. They're both going to be real. Andy?
Gonna have a multiplicity of 2.
Yes. Remember when we had repeated roots and the multiplicity told us how many times the root would appear? We have 1 real root here, but it has a multiplicity of 2. So now, since we've kind of dissected these graphs a little more, we can see that all of these quadratics do in fact have 2 solutions. Even though the graphs might not look like it, they do have 2 solutions. And right there it shows you the factoring of each equation. The first one, x squared minus 4, that's a difference of squares. And you get 2 and negative 2 as your real roots. The second graph in the second quadratic was x squared minus 2x plus 1. And that factors as a perfect square trinomial, x minus 1 times x minus 1. So that's where we get our multiplicity of 2. And then the last quadratic was x squared plus 2x plus 2. That factoring looks a little crazy. How would we actually find the solutions to that x squared plus 2x plus 2? Because we can't just factor that using the regular method. What would we do? What would we use to solve that quadratic? Tom? Yeah. We would use the quadratic formula for this guy. And that's how we would end up with our two complex roots. Remember, complex roots just mean that we are using I. So it could be something like 7i, could be something like 1, or something like I square root of 3, 4 plus I square root of 2. Complex roots just mean we're using I. So here it is, the fundamental theorem of algebra. It should be a little longer and more complex, don't you think? It's just so simple, just one little word, one little sentence. It's the whole fundamental theorem of algebra. If p of x is a polynomial of degree n greater than or equal to 1, so we've got a polynomial to the nth degree, then that polynomial has exactly n roots, including multiple and complex roots. So all the fundamental theorem of algebra is saying is the degree of your polynomial tells you how many roots you have. The degree of the polynomial tells how many roots that polynomial has. So, a quadratic polynomial, it's going to have 2 roots. A cubic polynomial will have 3 roots. A quartic polynomial, 4 roots. And so on and so forth. And we could go on and on and on and on and on. Now, why is it that sometimes on a graph it's not going to look like you have that many roots? Because of multiple roots and complex roots. The multiple roots and complex roots are why sometimes on a graph it's going to look like, hey, I only have 4 roots and I'm supposed to have 6. That's because there's a multiple root there and or a complex root. Let's do some problems. It says, determine how many roots the polynomial will have, then find all of the zeros. So, how many roots will this polynomial have? Connor, how do you know that?
The first term next to the
Yeah. Our highest degree is 5, so how many roots? 5. And I'm just going to kind of write it up there. How do we usually find roots from a polynomial? What do we do to find the roots of a polynomial? Chelsea? Right. And we need to factor this. Whew. A pretty big guy to factor now, isn't it? Okay. We're going to use everything we have learned from Chapter 4, from Chapter 5. We're going to use all kinds of different varieties of things to factor this guy and to find these zeros because we have to find 5 of them. What would be an easy way to find these that would not include factoring by hand? What could I use? Maybe on my iPad, maybe over there. What could I use? Graphing, exactly. So all we have to do is, if you guys would want to, you can use the graphing calculators, but Quick Graph will do the same thing for you. Let's throw this into a graph and see what happens. And by graphing, we just found x equals -2, x equals 1, and x equals 2. Now, if you think you might forget how we got there, just make yourself a little note. Use a graph. Now we need 2 more roots. We have 3 of the 5. Anybody have any ideas? What did we do in the last section to find out if things were factors? Connor?
Synthetic division.
Yeah. You already know some of the factors of this polynomial, right? Since you know those zeros, you know that x plus 2, x minus 1, and x minus 2 are factors, correct? Because those are zeros, we know that those 3 are also factors. Now, if we do what Connor said and use those factors with synthetic division, we can eventually come to our final answer that we can set equal to 0 and find the other 2 roots. So what we're going to have to do is we're going to have to do synthetic division a couple times. Let's take, it doesn't matter which one first, just take one of your factors. I'll take the x plus 2 just because it's the first one listed there. So if I'm going to divide this big polynomial, x to the 5th minus 4x, yada, 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 if I'm going to divide that big polynomial by x plus 2, I'm going to use synthetic division. So remember, synthetic division, we take our factor, we take our divisor, and we switch its sign. So instead of plus 2, we have minus 2. Now write all of the coefficients of the polynomial. 1, negative 1, negative 3, 3, negative 4, and 4. Bring your first value straight down. So then we multiply that value, that 1, times the divisor. 1 times negative 2 is negative 2. And then add your column to get negative 3. Take that negative 3, multiply it by the negative 2, and you get 6. Add that column to get 3. Multiply 3 times negative 2, you get negative 6. Add that column. 3 plus negative 6 is going to be negative 3. Multiply negative 3 times negative 2. 6. Add that column, you get 2. Two times negative 2 is negative 4. And this is a good sign here. Because 4 plus negative 4 is 0. Why does that number have to be 0? Tom? Exactly. And if we're dividing and we're trying to find a factor, we want no remainder. Okay. All right, guys, ready for this? I didn't say this was a short process. Now, we have to think, okay, so from here I have, that would be my constant linear quadratic cubic quartic. This would be x to the 4th minus 3x cubed plus 3x squared minus 3x plus 2. After all of that division, I got myself to a quartic polynomial. So these numbers right here are just your coefficients. We always start remainder, constant, linear, quadratic, and we just count up from there. Can we factor that? X to the 4th minus 3x cubed? We really can't. What should I do now? Ryan knows. What should we do now, Ryan?
Do the next one.
Divide again. So we're going to take our next factor. So this time I'm going to divide the polynomial I had just got. I'm going to divide this guy by my next factor, x minus 1. Switch the sign of your divisor. List your coefficients. And then it's just synthetic division all over again. And we get x cubed minus 2x squared plus x minus 2. All right. I still can't factor this because the only way I know how to graph cubics right now is if they are the difference of cubes or the sum of cubes. This is not. So we have to do it one more time. So I'm going to take this polynomial I have and divide it by my last factor, x minus 2. Switch the sign of the divisor. List the coefficients. And what we get is x squared plus 1. Remember that 0 there would technically be x squared plus 0x plus 1, but we don't need to write 0x. We can just write that as x squared plus 1. Now finally we have something that kind of looks like maybe I could factor this. But even if I can't factor it, I can solve it. Because all I have is a square root here. Or a square, which can be undone by a square root. Now usually, if you have two terms and you have perfect squares, which we do, you think, hey, I can do difference of squares. You can't. This is the sum. You cannot do sum of squares. But you could very easily take this factor, x squared plus 1, set it equal to 0. So x squared equals negative 1. What's the square root of a negative 1? Connor? Yes. So we get x equals plus or minus I. So we have plus or minus, that's two answers. Then we have our three factors, negative 2, 1, and 2 from the top. So then we have all 5 of our factors. Why is it that we could only see the top factors on our graph? Because the other zeros, the other solutions, were imaginary. See? One was positive and one was negative I. So they're not going to appear as x-intercepts on your graph. So there's the fundamental theorem of algebra. We know we needed 5 roots, and now we've just taken a whole bunch of steps to find those 5 roots. Now, to make you guys really happy, we're going to do one more problem before we leave. Problem number 2. How many roots should this guy have? Dom? Right? And what we always want to try first is, hey, can we put this on a graph to find some roots? But what do we need to do before we put this on the graph? Connor? Right. X to the 4th plus 2x cubed minus 13x squared plus 10x. And once you have that, you guys can go ahead and put it on your graph. Because all of our roots were x-intercepts, x equals -5, x equals 0, x equals 1, and x equals 2. They were all real answers, all right there on the graph. So there we have it, our 4 roots from the graph.